Welcome everybody to Calculus BC. In today's episode, we're going to be discussing chapter 9.2, which is the introduction to series. And we're going to be going over only a few different types of series in this particular episode. And then we will continue on with series as the chapters continue to move forward. And so fundamentally, a series is just the sum of a sequence. So in the last chapter, we had things like we had something like this. We had something like 3, like negative 6, 12, and negative 24, and then dot, dot, dot. That was a sequence, right? It was just a bunch of terms that were following literally sequentially after each other. But in a series, it's going to look more like this. 3 minus 6 plus 12 minus 24, and then plus dot, dot, dot. And it's just going to keep on going until we tell it to stop, or it may never stop if we have it go to infinity. And so what we're going to do here is we're actually going to start off with evaluating this series right here, because this one's a pretty familiar one. We've seen this before in integrated 3, where if it looks like the terms are increasing in a certain way, they very likely are, because these series and sequences increase or decrease by a specified pattern. In this case, this one looks geometric because the ratio between the terms looks like it's negative 2. Again, looks like we're multiplying by negative 2 each time. Multiplying by negative 2 here. And so so the way we're going to figure out the sum of this series here is we're going to use a formula. And the formula is derived by looking at the sum of some amount of terms. That's why they call it S sub n. So it's like the sum of n terms, where like if n was 6, we'd be doing the sum of 6 terms and whatnot. We would know that sum would be a sub 1, right? In other words, the first term. In this case, that would be 3. And then it would be plus a sub 1 times r, right? The ratio. And that's how we were able to get this negative 6, right? So it's the 3 times negative 6. And then we would take this term here, this a sub 1 times r, and we'd multiply it by another r, making it r squared, and then r cubed, and r to the 4th, and blah, blah, blah. So down the chain we go, and I'm going to end it with the final two terms. Now, I'm going to call it something a bit odd. A sub 1 times r to the n minus 2, and I'm going to end up with a sub 1 times r to the n minus 1. Now, if you're wondering why I'm not ending with a sub n, there's a reason for that, and it really helps just make the extrapolation easier to look at. And so from here, what I'm going to do is I'm going to take that sequence again, and I'm going to take it again, s sub n, and this time I'm actually going to multiply it by the letter r, just the letter r right here. So all of those a sub 1s are going to come down, and all the original, so all the a sub 1s are going to come down, a sub 1, a sub 1, and then dot, 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 a sub 1 plus a sub 1. But when I multiply everything by r, everything gets elevated by an r. So r cubed, r to the 4th. And this r to the n minus 2 becomes r to the n minus 1. And this guy here, if I multiply him by an r, he becomes a sub 1 times r to the n. And that's why I ended it with n minus 1 this time. It just makes it easier to kind of conceptualize what's going to happen in the next move here. And so what I'm going to do is I'm going to take these two series, I'm going to subtract them. So I'm going to say s sub n minus r times s sub n. So again, the top series minus the bottom series. If I subtract the entirety of this, what happens is that everything that's positive is going to go negative. And what that does is it allows for a diagonal subtraction of everything all the way down. This guy will cancel presumably with an r time raised to the n minus 2 down the chain, and then these guys will cancel, leaving me only with the first and last term surviving, which is going to be a sub 1 plus a sub 1 times r to the n. On either side, I'm going to factor out their respective GCS. So I'm going to factor out an s sub n. That leaves me with 1 minus r. I'm going to factor out an a sub 1. That leaves me with 1 minus r to the n. And again, the whole time I've been trying to figure out a formula to find out the s, right, the sum of the fixed amount of terms here. So I just divide both sides by 1 minus r. So I have a sub 1 times 1 minus r to the n divided by 1 minus r. And this formula right here, this is the finite geometric series right here. So we remember this from integrated 3, hopefully, the finite geometric series. And that's the way we find the sum of the say the first 24 terms of a particular geometric series. As long as the series was geometric, we could find out the sum of 24 terms or the sum of, 8 terms. But in this case, I'll have us go ahead and find out the sum of 10 terms here. So this one would look like S sub 10 would be equal to A sub 1, which is the first term. That's going to be where this 3 comes from. So this 3. And then 1 minus r. So remember, r was negative 2, and that's going to get raised to the 10th power because we're doing 10 terms, all over 1 minus negative 2. Now, if you have the time, just put that in the calculator, and then you will end up getting a number. And give me a second. I will find out what that is in just a second. And after some button pushing, I don't want to waste much time here. I got negative 1023 as the answer. So hopefully that makes a certain degree of sense right there. Again, I just punched into a calculator, and that's all I did. Okay, so the finite geometric series is all good and dandy. However, one of the things that is going to become more prevalent as we move forward with series is not the notion of a finite series. It's actually the notion of the infinite series. We've been doing a lot of work in the sequences portion regarding convergence and such. We're going to do the same thing here. What do we approach? Like, what does our sum approach as we are approaching an infinite number of terms? And so if we look back at this formula here, this S sub n equals A sub 1 times 1 minus r to the n over 1 minus r, there is actually a possibility that the r could actually go away. And if I said if the absolute value of r was less than 1, let's say, for example, if I said let r equal 1/2. If I took 1/2 and raised them to, say, the trillionth power, because I can't really plug in infinity, right? And 1 trillion isn't even the biggest number we can think of. We could think of 100 trillion or 5,000 trillion, whatever that next iteration up would be. I would get 1 over 2 to the trillion, and that is super, super, super small, right? So as my n goes to infinity, again, 1 trillion isn't even close to the biggest number we could think of, the r would actually go to 0 as long as if the absolute value of r was less than 1. So what happens is that when we take the infinite geometric series, we get s, and instead of s sub infinity, we just say s, like the infinite, and we call it the infinite geometric sum. This guy would go to 0, again, as n goes to infinity, r goes to 0, leaving me just with a sub 1 over 1 minus r. And this right here, is the infinite geometric series right here. So infinite geometric series. And again, the stipulation of this really is, the stipulation of this really is that the absolute value of r does in fact have to be less than 1 in order for this to happen. Because imagine if the r value was, say, 4/3, right? And if I took 4/3 to the trillionth now, 4/3 to the trillion, well, clearly that's going to grow and explode into infinity, and that's going to cause the sum to diverge. So we definitely want that r value to be less than 1. So how does this play out in the infinite geometric series world? Let's say I gave you an example of, say, 5 minus 10/3 plus 20 over 9 minus 40 over 27 plus ... And now I want you to find the infinite series, the infinite sum of this thing. Well, just figure out what a sub 1 is. That's pretty easy. It's 5. R is, I think, is kind of odd, but I think if we just kind of look at the top and bottom individually, we could all agree it's going to be negative 2/3. And since the r value is, the absolute value of the r value is less than 1, what would happen is we would just say, okay, well, the sum can be found. So we have 5 over 1 minus negative 2/3. And if we just punch all that stuff in, we end up actually getting 3. So what happens is that this sum converges towards 3 when we take its infinite sum. And I think that's actually kind of neat, right? The terms are going to converge into a place where we end up getting a final sum of 3. And we've seen a lot of examples like this before where you're adding up like this infinite square. And it turns into an area of 1. It's pretty neat. Okay, so give me a second. I'll be right back with some more examples. Sometimes you're given a geometric series and it's not clear that you're dealing with a geometric series. And so when that happens, you're going to have to use a little bit of algebraic manipulation in order to turn it into something that you can recognize. So I'll start off with sigma notation here. I'm going to call them 2 to the 2n times 3 to the 1 minus n. Now, what I am not allowed to do is I am not allowed to take these series individually and then multiply the results together. That's not how this is going to happen. If they were being added, I could totally do that, but unfortunately that's just not the case. So, understandably, you probably wouldn't believe me if I told you that this was a geometric series. But let's see if we can algebraically manipulate this into one. So what I could do is, since these two exponents, the 2 and the n, are being multiplied, I could call this 2 squared raised to the n. And then I can go ahead and flip and factor out a negative on that 3 right there. So what that allows me to do here, if I just carry down my sigma notation here, that allows me to call the inside piece here 4 raised to the n. And then the 3 to the negative version of n minus 1 can go down to the bottom. And again, I'm just using some exponent rules here. So this is actually not much more advanced than an integrated 1 problem. And then from here, I'm going to go and separate the way we do with the exponential growth problems. I'm going to call this 4 to the n over 3 to the n times 3 to the negative 1. Again, sigma here, n equals 1 to infinity. Now, this 3 to the negative 1 will, in fact, kick up to the top. However, like we do, or rather like I do in integration or in derivatives or a lot of things calculus-based, the constants I tend to kick way on the outside. So you can kick that constant all the way on the outside of the sigma and just call him, instead of 4 to the n over 3 to the n, you can call him 4/3 all to the n. And what that allows me to do here now is it allows me to say, okay, what's a sub 1? Well, in this case, we have 4 over 3 raised to the n, not to the n minus 1. So if I plug in a 1, I'm going to end up getting 4/3 times 3, so my a sub 1 is 4. My r value is 4/3, which means this thing diverges, right? The absolute value of r, in this case, is greater than 1, and therefore the geoseries diverges. And that's where you want to be with this one here. So again, it's that whole idea, just rewriting a geometric series, that way you can kind of see it in a bit of a different frame. That way, when you work with it, you can easily identify this as a geometric series. Sometimes they give you variables instead of numbers. So if they ask you for something like this, like say example 3 here, if they say from n equals 1 to infinity, one of the tougher elements of the series portion is when they introduce new variables. You've got to know what is a variable and what is a constant. And in this case, x plays the role as the constant, and n is the role of the variable. So what we're going to do here is we're going to write down the first 5 terms, and we're going to find the sum. Now, this thing here relies heavily on this fact right here, right? Notice how they told you that the absolute value of x was less than 1, which means the sum is going to be possible. And so what we're going to do is I'm going to write out the first 5 terms. So it looks like I got x, x to the, oops, and I made a mistake here. That actually started off at 0 here. X to the 0 plus x to the 1 plus x to the 2 plus x to the 3 plus x to the 4. Okay, so here we go. Here's where we're at right here. X to the 0 is 1 plus x squared plus x cubed plus x to the 4th. And now I'm going to figure out what my ratio is. My ratio is equal to x. So that means that my sum is going to be 1, which is my first term. And then my ratio, or the piece on the bottom, is going to be 1 minus x. And that is your sum of this particular geometric series. Okay, I will be right back with another example. Give me a second. Using the notion of partial sums, what we use partial sums for is, unfortunately, not all series are geometric. And so, when they're not geometric, it's going to be hard to find out exactly what that sum is, because the only sum we can find an actual number for is going to be geometric, but we can find out what the sums are going to converge into as long as we were given a formula to find out what those terms are approaching. So from here, if I gave to you some series, right? So S sub n equals some term a sub 1, some term a sub 2, some term a sub 3, and then plus ... And then I said plus sum a sub n, right? So the sum of terms up to the nth term would lead me to the nth term, and I know that that series, the sum of all this stuff here, would equal 2n over 3n plus 5. What we have to do is we have to figure out what is the role of this. Like this thing here, what is this? Well, if we just get rid of the middle piece here, if we just said, hey, we don't need you, we don't need the physical representation of this sum, we just know that if I added up all those things that I just crossed off, I would end up with 2n over 3n plus 5. And what this is this right here. This is the nth partial sum of that series that I just crossed off right there. So if I wanted to find, say, s sub 5, wouldn't be too hard, right? I would just plug in a 5 to find out the sum of the first 5 terms. If I wanted to find s sub 30, wouldn't be too hard. I could do 2 times 30 over 3 times 30 plus 5. Again, right, this formula gives me the nth partial sum, right? So it is the result of all of the additions together. But if I wanted to find the infinite part, if I wanted to find the infinite sum of this series, if I said, hey, just find out all the terms that go to infinity, well, here's what I can't do. I can't go s sub infinity equals 2 times infinity over 3 times infinity plus 5, right? Again, we're not in the business. We can't plug in infinity here. But what we can do is we can hearken ourselves back to a topic that we learned a while ago, and that was the improper integral, right? And the improper integral said that if I had the integral from 1 to infinity of, say, f of x dx, right? Obviously, the integral playing the role as the area under the curve, or the summation of rectangles of infinitely small rectangles underneath the curve. We can't add up infinity, but what we did do is we assigned a variable that would approach infinity infinitely closely. So I used n before, and we would do from 1 to, not infinity, to n, and we would do f of x dx. And we would take the limit after we did the integration portion, and we would end up getting a value. So we would know that the area beneath the curve approached a particular value infinitely closely. And so what I'm going to do is I'm going to employ that tactic here to partial sums. So instead of doing s sub infinity, I'll just say s sub n is equal to the limit as n goes to infinity of 2n over 3n plus 5. And so what I can do here is I can go ahead and use some algebraic mumbo jumbo here to get the limit as n goes to infinity of 2 over 3 plus 5 over n. We're just kind of going back to Calc AB right now, and we end up with very expectedly 2/3. So what that's saying is that the sum of the infinite series would approach that 2/3 infinitely closely. And so again, this formula here, I just want to remind us, this formula represented the nth partial sum. And this time it was really clear because we were given a formula to find out a partial sum. That won't always be the case, but in this particular chapter, I believe that is always the case. So moving on to future chapters, that might not happen all the time. So hopefully that makes sense. I'll be back with another example. The last type of series I want to introduce you to is something called the telescoping series. And it's a bit odd, but there's a reason why I taught you all about partial sums before jumping into the telescoping series. And that's because we're going to use partial sums to come up with a partial sum formula for this. That way we can take the limit of it, and the limit of the partial sum formula, as we saw in the last example, will get us the infinite sum of the series. And so if I gave you something that looked like this, from n equals 1 to infinity of 1 over, let's say, n plus 2 times n plus 3. If I expanded the first couple terms, I would do 3 times 4 plus 1 over 4 times 5 plus 1 over 6 times 7 plus ... And so from here, this pattern just keeps on going. So what I'm going to do is I'm going to try and find out what the nth partial sum would be. So to do that, I'm going to go ahead and reframe this a little bit. I'm going to say the sum from k equals 1, so just a different variable here, to n. And I know that s sub n, like the sum of the nth term, and the sum of n amount of terms, rather, would be this. So then that's going to become k plus 2 times k plus 3. And again, I'll just go ahead and repeat the first step here. So 3 times 4, 4 times 5, 6, 6 times 7, and then plus dot dot dot, and it's going to finally end up with 1 over n plus 2 times n plus 3. And this is my nth term right here, right? And so to find out the nth term will allow me to figure out the fixed sum or the finite sum of this thing. So let's take a look at this from a different perspective. If I was to want to separate these fractions out, like 1 over k plus 2 times k plus 3, and you guessed it, if I'm going to separate these out, I'm going to end up having to use partial fractions on this thing. So a over k plus 2 plus b over k plus 3. Well, a times k plus 3 plus b times k plus 2, that's going to equal 1. So if I let k equal negative 3, that's going to go away here, but b will equal negative 1. If I let k equal negative 2, well, that guy's going to go away, and I end up with a equaling 1. So what this is telling me is that the sum of the n number of terms can start from k equals 1, and it'll go to n. And what I've got here is I've got a over k plus 2, so 1 over k plus 2 minus 1 over k plus 3. Now, the reason why we're separating the fractions here is because I think it's going to make things a little bit more manageable in terms of what's going to happen with this partial fraction or this telescoping series here. So I end up with 1/3 minus 1/4 now if I let k equal 1. I have 1/4 minus 1/5 now. 1/5 minus 1/6, 1/6 minus 1/7, and then dot dot dot. Now remember, it's a telescoping series, right? Where this two-term expression here is the result of k equaling 1. This whole thing is the result of k equaling 2. This whole thing is the result of k equaling 3. This whole thing is the result of k equaling 4, and dot dot dot. And so remember, a series takes those terms and it adds them together. And ultimately, we end up with plus 1 over, looks like n plus 2, and I'm going to have to move over just slightly to the right here, minus 1 over n plus 3. And again, this happens at my nth term. And so now from here, I think we're going to see something kind of interesting happen, where I'm going to get 1/3 minus, now I'm going to go ahead, actually 1/3 plus, and I'm going to go ahead and group things together that deserve to be grouped together. So negative 1/4 plus 1/4 plus negative 1/5 plus 1/5 plus negative 1/6 plus 1/6, and I think you see where this is going here. And so what's going to happen is down the chain, I hope it makes sense that in line with this 1 over n plus 2 is going to be a negative 1 over n plus 2 behind it, and then the negative 1 over n plus 3. And so all these middle guys are going to cancel each other out, and what I have is I have a formula called S sub n, and like I did before, I'm going to get rid of this middle guy here, and I'm going to say that this is 1/3 minus, or rather plus 1 over n plus 3. And what I've just found here is this is the nth partial sum formula. And the way we find out the nth partial sum, again, from here I can find out the sum of 50 terms, the sum of 1,000 terms. But in this case, I'm going to take the limit as n goes to infinity of s sub n. And that is the limit as n goes to infinity of 1/3 plus 1 over n plus 3, which simply means 1/3. So if you're wondering why this is called a telescoping series, it literally is because all of the terms in the middle cancel each other out as if you were folding down a pirate's telescope. So hopefully that makes sense. I'll be right back with another example because the next telescoping series can get a little weird. All right, in the last example here, I'm actually going to start off with something like this. I'm going to start off with n equals 2 and go to infinity, and I'm going to say 1 over 2n plus 1 minus 1 over 2n plus 5. Now, I'm going to skip over the partial fractions decomposition. We're just going to give it to you like this. And the reason why this is actually difficult is because of how it expands. So the way that's going to look is if I was to expand this thing, it would be 1/5 minus 1/9 plus 1/7 minus 1/11, and then plus 1/9 minus 1/13. So this is the first three terms right here. So this is what happens. This is what happens when n equals 2. This is what happens when n equals 3. And this is what happens when n equals 4. Again, I started at 2 because the series told me to begin at 2. Now, what's odd about this one is, if you notice, the 1/5 has nothing that cancels out, but that's normal. But the 1/9 doesn't start to cancel until this term here, until the third iteration of this partial series here, and leaving me with a 1/7 and a 1/11 that's kind of surviving. So when this starts to happen, when you end up with what I call skippage in the telescoping series, it really helps to just expand as much as possible until you start noticing a pattern. So in my opinion, we haven't gone far enough to notice any kind of discernible pattern when it comes to this telescoping series. So I'm just going to keep on going for a little while, and hopefully it doesn't get too annoying, but we will see what happens here. So now from here, what I've got is, after the 1/9 minus 1/13, I'm going to go ahead and say the next term is going to be 1/11 minus 1/15. Again, the 1/11 can now cancel out, but now I've still got some things that are surviving. And so let's just keep on going here. I'm going to go ahead and do one more term here, and that's going to be 1/13 minus 1/17. So again, what is this? This is when n equals 5, and this is when n equals 6. So let's see what's going to start canceling here. I'm going to go ahead and just lightly cancel out the 1/9. I'm going to start lightly canceling out the, looks like the 1/7 seems to survive. It doesn't seem to go anywhere. The 1/11 seems to go away. Down the chain, the 1/13 seems to go away. And I have every reason to suspect that the 1/15 will cancel down the chain, and then now I'm starting to develop some reasonable expectation here where the 1/17 will eventually cancel down the chain. I'm thinking the 1/7 and the 1/15 will probably survive. The 1/5 and the 1/7 will probably survive everything. Like, right, if there was something that was going to cancel that 1/7, it would have shown up by now based on the cancellation of the other pieces. So the way I'm going to do this is I'm actually going to break this down into literal partial sums. So I'm not going to come up with a formula just yet, but I am going to go ahead and say, so what happens when I do the second partial sum? In other words, when n equals 2. Well, that really is just 1/5 minus 1/9, right? And then when I do the third partial sum, which is going to be the summation of all of these guys, that's 1/5 minus 1/9 plus 1/7 minus 1/11. And the fourth partial sum is going to be 1/5 minus 1/9 plus 1/7 minus 1/11 plus 1/9 minus 1/13. And that's when I'm going to start seeing some cancellation happen. The fifth is going to be, again, 1/5 minus 1/9 plus 1/7 minus 1/11 plus 1/9 minus 1/13 plus 1/11 minus 1/15. And again, I'll just go and do the sixth partial sum because we went to 6 terms. I'm just going to go and list them out individually and there's a reason why I'm doing this. It's because I want to come up with some common ground as to what's surviving, what's not, and how we can come up with a formula for what can survive on the back end, because that's eventually where we're going with this, right? We're going to try and find what survives on the back end of this thing, so that way we can pirate telescope this thing downward. So 1/9 minus 1/13 plus 1/11 minus 1/15 plus 1/13 minus 1/17. Okay, so let's just go through the chain and see what survives here. So in S sub 2, both of these guys survive. In S sub 3, looks like they all survive again. But in S sub 4, that's when things start to cancel. Things start canceling at this marker right here. So I'm going to go and cancel the 1/9, and that's about it. In S sub 5, the 1/9 cancel each other out. The 1/11s look like they're canceling each other out, and I think that's all I've got here. Here, the 1/9s cancel each other out again, the 1/11s, the 1/13s, and I believe there is another thing in there that cancels out. Am I looking at it right? I don't see it. Okay, but eventually down the line, it looks like a 1/15th would cancel out and a 1/17th would cancel out. So let's take a look at what's surviving here. It looks like 1/5 and 1/7 always survive. The 1/5 survives here. The 1/5 survives here. 1/7 survives. 1/5 and 1/7 survive. It seems like they just survive everything. Okay? And so now let's take a look at what survived in each category here. So starting with S sub 4, that's when things started to kind of cancel out. So it looks like a negative 1/11th and a negative 1/13th survived. In S sub 5, a negative 1/13th and a negative 1/15th survived. And in S sub 6, negative 1/15th and negative 1/17th seem to survive. So let's see if we can come up with a formula that allows this to happen. Well, I know it's going to be negative 1 over something here. And since I'm at the fourth term here, does it make sense, hopefully, that I have to multiply something by 4 and then add something else to get to 11? Well, how do I do that? Well, it looks like the slope here between the terms is 2. So I'm thinking it's 2 times 4, right? That would be 8 plus 3. So that means that negative 1 over, would that be the same for here? 2 times 5 plus 3. That seems to work. So negative 1 over 2 times 6 plus 3. So I'm thinking that the formula here is negative 1 over 2k plus 3. And then the next one is going to be the same thing. So it's going to be negative 1 over, again, the slope seems to go up by 2 each time. So it's linear. So that looks like it's going to be 2 times 4. But this time I'm going to have to add 5 each time. And I feel like that's going to be the same for all of them. So that means negative 1 over 2k plus 5. So what that means is that I've got a summation. And that's going to be 1/5 plus 1/7, because they always survive. But then the negative 1 over 2k plus 3 will survive on the back end. And the negative 1 over 2k plus 5 will survive on the back end. Which means if I take the limit as n goes to infinity of my S sub n, I will get these guys to cancel, and I end up with 1/5 plus 1/7. Hopefully that's not too confusing, the skippage telescoping sum. But for now, that's where we're at when it comes to sequences and series. We are at geometric, we are at partial sums, and we're at telescoping series. And so hopefully you're not totally confused. But as always, please leave comments or questions in the comments area. I will see you all in the next episode.